All right, let's talk about something really cool. How do you actually teach a computer to see a pattern? To look at a bunch of data and predict something like a house price or next month's sales. Well, today we're going to crack the code on one of the most foundational tools for this, linear regression. Let's get right into it. Yeah, really, this is the core question, right? You've got this cloud of data points, and you know there's a story in there somewhere, but how do you get a machine to find it? Not by guessing, but with a solid mathematical approach. So, where on earth do we start? Believe it or not, this whole complicated field really boils down to one super simple goal. We're going to tell the computer, make a guess. Then we'll measure how wrong you were, and your only job is to make that wrongness, that error, as tiny as mathematically possible. Okay, so first up, finding the best line. We've got to start somewhere, right? So let's begin with the simplest pattern you can possibly imagine, a good old-fashioned straight line. How do we draw the absolute best one through a bunch of scattered data? So just imagine you've got your data scattered on a graph, just like this. You and I could probably eyeball it and draw a line that looks pretty good, right? But there are literally infinite lines you could draw. Some are clearly terrible, but a whole bunch of them might seem okay. Pretty good isn't going to cut it for a computer. We need a rock-solid mathematical way to define what best actually means. And here it is. This is our definition of best. It's called squared error. For every single data point, we just measure how far away it is from our line. That's straight up and down distance. That's the error. But here's the clever part. We square that number. Why? Well, by squaring it, we punish the big mistakes way more than the small ones. Think about it. Being off by 2 isn't just twice as bad as being off by 1. It's 4 times as bad. This makes the model really hate being way off on any single point. So, the whole game is this. You imagine drawing those little squares for every single data point based on our line. Then you add up the area of all of them. The best line, it's simply the one line out of all the infinite possibilities that makes the total area of all those squares as small as it can possibly be. That's it. That's our champion. It's why we call this the least squares method. Okay, so we've got the straight line down pat. Awesome. But you know the real world is messy, right? It's rarely a perfect straight line. So what happens when the pattern we're trying to find has curves and bends in it? Yep, exactly. Look at this. Trying to fit a straight line to a pattern that's clearly curved, it's like trying to hammer in the screw. It's just the wrong tool for the job. No matter where you put that line, you're going to have a huge error. Our model's just too simple, too rigid. So how do we give our simple model the power to bend and curve? The answer is an absolutely brilliant little trick called basis functions. Here's the idea. Instead of just giving the model our plain old input, x, what if we also give it a transformed version, like x squared? The model itself doesn't change. It's still just finding the best weights for its inputs. That's why it's technically still a linear model. But because we cleverly engineer the inputs, the final result can be this gorgeous, complex, nonlinear curve that fits the data perfectly. And we've got a whole toolbox of these things. We can use polynomials, x, x squared, x cubed, to create all sorts of waves and curves. We can use Gaussian functions, which are basically little bell curves, to capture effects that only happen in a specific region. Or we can even use S-shaped curves. Each one of these is like giving our model a new superpower, a new way to bend and twist to match the data. All right, so let's recap. We have a model, we can even make it flexible, and we have a clear goal, minimize that squared error. But now we hit the really practical question, how does the computer actually do it? How does it find the perfect settings that get us to that minimum error? Well, when it comes to finding the bottom of that error valley, we've basically got 2 main strategies. The first is the direct approach. It's like a super-powered math equation that just solves for the answer in one single clean shot. The other way is more like a journey, an iterative approach called gradient descent, where we find the answer by taking a series of smart steps. And this hiker analogy for gradient descent, it's honestly perfect. Just picture it. You're standing on a huge, foggy mountainside. Your goal is to get to the absolute lowest point in the valley, but you can't see more than a few feet in front of you. What do? Well, you can feel the slope of the ground right under your feet. You can tell which direction is the steepest way down. So you take one small, careful step in that direction, and then you do it again. And that little story is literally the entire algorithm. Step 1, you start with a totally random guess for your model settings. Step 2, you calculate the steepness of the error right where you are. That's called the gradient. The gradient technically points uphill, So, for step 3, you take a small step in the exact opposite direction, downhill. And step 4, you just repeat again and again and again, one small intelligent step at a time until you get to a flat spot where you can't go any lower. Okay, but there's a huge catch, a big practical problem. To figure out the true steepest direction, to calculate that gradient perfectly, you have to check your error against every single one of your data points. Now, if you have a few hundred points, no big deal. But what if you have millions or billions? Each tiny little step would take forever. It's just way, way too slow. So what's the solution? It's called stochastic gradient descent, or SGD, and it's another clever workaround. Instead of looking at all million data points for every step, what if we just grab a small, random handful, maybe 32 or 64 of them, and calculate our downhill direction based only on that little batch? Now, is that direction perfect? No. It's going to be a bit noisy, a little wobbly, but it's so ridiculously fast to calculate that we can take thousands of these wobbly steps in the time it would take to take one perfect one. And it turns out, all those fast, slightly off steps still get you to the bottom of the valley, and usually much, much faster. Okay, so now we have these super flexible models that can learn complex curves, and we have a really fast way to train them. We're feeling pretty powerful, right? Well, with great power comes a pretty big new problem that we have to be super careful about. And that problem is called overfitting. It's what happens when our model has too much power. It gets so flexible that it doesn't just learn the real underlying pattern in the data, it starts to memorize the random noise too. The analogy of studying for a test is perfect here. Overfitting is like memorizing the exact answers to the practice questions instead of actually learning the subject. You'll ace the practice test for sure, but when you get the real exam with new questions, you're going to fail hard. So how do we stop our model from going wild and memorizing noise? We use a technique called regularization. And you can think of it like putting a leash on your model. Here's how it works. While we're training, we add a new rule to the game. On top of trying to minimize the error, we also add a penalty for complexity. It's like telling the model, look, I want you to fit the data well, but I also want you to stay simple. Don't use your crazy complex powers unless you absolutely have to. And there are a couple of popular ways to apply this penalty. The two big ones are ridge and lasso. Think of ridge as a gentle leash. It just kind of pulls back on all the model settings, shrinking them all a little bit to keep things from getting out of control. But lasso is different. It's a much more aggressive approach. It doesn't just shrink the weights, it can actually force some of them to go to exactly 0. And this is a huge deal. It means the model is literally learning on its own which inputs are totally useless and just throws them away. It's doing automatic feature selection, which is just incredibly powerful. Alright, this brings us to our final section. And honestly, it might be the single most important idea in all of machine learning. It's the fundamental conflict, the one big trade-off that we are always trying to manage. And that conflict is the bias-variance trade-off. Seriously, everything we have talked about today, from choosing a simple line versus a curvy one, to using regularization to tame complexity, it all comes back to managing this one core concept. So here's what it breaks down to. Your total error really comes from two different enemies. First, you have bias. That's the error you get when your model is too simple, when it's just underfitting. It's consistently wrong in the same way because it just doesn't get the real pattern. Your other enemy is variance. That's the error from a model that's too complex and overfits. It's way too sensitive to the random noise in your training data, so its predictions are all over the place. And here's the killer trade-off. The moment you try to fight one, you usually make the other one stronger. Reducing bias by making your model more complex almost always increases its variance, and vice versa. And so that leaves us right here, with the question that is at the absolute heart of machine learning. In this world of messy, complex data, how do we find the model that's just right? The entire job, really, is navigating that trade-off.